So here we are, my lovely students, back. We are looking at section 3.4. This will finish out chapter 3 for us. So what we're looking at now, we just finished looking at inverse functions in general, which was a review from your previous algebra courses. Now we're going to take that concept and apply it to the trig functions. So when I know that the sine of theta is 1/2, I can look that up in the unit circle and I can see what theta is. But what if I have this? Now it's a nice pretty fraction, but that fraction doesn't appear as one of our listed points on the unit circle chart. What I can do is use the inverse of sine to figure out what the angle measure is. So in math, we'll use these functions for other things, but like real world applications, this is the kind of thing where it's like, if I'm going to be constructing a triangle out of wood, and I've got this side and this side, and I need to figure out what angle to cut the wood at so it'll like span on the hypotenuse correctly, you'd end up using something like this. So inverse sine, or it's sometimes pronounced arc sine, but we write it sine -1 usually. So I am not multiplying by sine -1 or arc sine. I'm applying arc sine to both sides the same way I can square both sides, or I could square root both sides. I could add a number to both sides. I'm not multiplying by sine here. Sine is not a number, sine is a process. So over here though, arc sine of sine are designed to cancel each other out. And then arc sine of 2/3 is actually something we can crunch on the calculator, and it'll spit back a result in radians or degrees depending on the mode we're in. The catch here is, for arc sine to work as a function, we have some restrictions that get imposed. So when you look at the unit circle, sine starts repeating itself. And then we know the whole graph like repeats itself a whole bunch. So when we're looking at our inverse functions, we can't look at the entire function and invert it. Kind of like we can't look at a parabola and invert the whole thing. We have to chop it. We're going to do the same thing on sine and cosine. Where we chop it is, so we would have a graph that is 1-to-1, that passes the horizontal line test. So we have to remove any spots where the graph like starts to double back. So with our sine graph, like normally the sine graph starts at 0, 0, goes up, back to 0, 0, goes down, back to 0, 0. So those first two sections, it's doubling back on itself. So instead of going 0 to pi, our domain is going to run from, or rather, the domain of sine, which will end up being the range of the inverse, is going to run from -pi/2 up to pi/2. Now our cosine graph, since it starts at 1, we can just take the next two sections. So the cosine graph runs from 0 to pi. So when we restrict sine and cosine to these little pieces, these restricted domains, we can find the inverse of those single pieces. So that's what we have next, is some pictures of these inverses. So let me kind of zoom in because these are weird to look at. So this darker blue graph here, like it has an arrow up to here, but it's the full sinusoidal graph. It's just, this is where we make our chop. And then that diagonal line, remember, we reflect across it. So where it hits here, it's going to hit here, that point, and then it'll go through pi over 2 up here, back to there. So this point is mirroring this point. On the regular cosine graph, this is a 1. Because it would come from up here. And then this one over here is a -1. So our inputs for inverse cosine, our inputs are what we could get out of the original function. So the domain of the inverse is equal to the range of the original function. Now remember, our cosine graph goes up and down, up to +1, down to -1. So the domain on the inverse is from -1 to 1. The range will run from 0 to pi. And that was, we got that from restricting our original cosine graph. Now, the other thing that pops up here is that little acronym, all students take calculus. So sine is positive in the second quadrant. Cosine is positive down here in the fourth quadrant. That means cosine is negative in the second quadrant, which is what we want. So that's why arc cosine uses the first two quadrants, because it has positive cosines and negative cosines. That way our inverse function can give us the largest number of answers. Like, it's got access to the full set. Now our sine, because it's positive in the second quadrant, we can't run 0 to pi, so that's why we ran differently. So what I do with my all students take calculus is I will sometimes like put in some lines. So like that green one there, that's where arc sine, and then we'll see in a minute that is also where arc tangent is defined. And then over here, that's where arc cosine is defined. Now, when I say is defined, what we're going to see that means is those are the only answers that inverse cosine can spit out. It will only ever give you a number between 0 and pi, or 0 and 180 degrees. It will not spit out a negative number. It will not spit out a number greater than 180. And then the same for inverse sine and inverse tangent. They're only going to spit out results in the fourth or the first quadrant. So negative angles, positive angles between negative pi over 2 to pi over 2. And again, we can see this dark blue graph. That's our regular sine graph. So our arc sine graph. It's going to throw down here, about 1. Here will be -1. And the values are from negative pi over 2 to pi over 2. So here it's just written out. All right, so inverse tangent or arctan. And some older books will actually write arc sine, arc cosine, and arctangent. It's just a holdover from when getting superscript on a typewriter was a pain in the ass. You could type arctan a lot easier than shifting it up and putting the -1 and then having to shift it back. And yeah, I know some of the stuff we do is weird. Now, arctangent, when you look at that graph, tangent actually has, the original tangent graph has asymptotes. At pi over 2 and negative pi over 2. Since tangent is sine over cosine, it's where cosine would be 0. So at pi over 2 and negative pi over 2. So the graph of tangent, like, actually will like shoot down to infinity. So our graph of arctangent is going to be the same. We're actually going to have some weird horizontal asymptotes, and the graph will get close but never touch. So our range on arctangent actually goes from almost negative pi over 2, so negative pi over 2 in parentheses, up to positive pi over 2 in parentheses. And the domain is all real numbers. So I can put whatever I want into arctangent and it'll spit out a positive or a negative answer. It's crazy, right? So here they just summarize. If we are looking at an angle between negative pi over 2 and pi over 2, then we can apply arcsine to get what the angle measure is. Our cosine will only work for values between 0 and pi. Tangent will only work for non-inclusive between negative pi over 2 and pi over 2. All right. So evaluating inverse trigonometric functions for special input values. Ew. Okay. So they're called special input values because these are numbers on the unit circle. All right, so if we go look for where is sine 1/2. So this is not our pi over 4 angles. So it's either pi over 3 or pi over 6. 1/2 is the short side, so I want the triangle that goes long short, which means this is the smaller angle of 30 to put a 1/2 there. So this is equal to 30 degrees or pi over 6. Now in your homework, they will tell you if they want degrees or radians. If you're not sure, go with radians. That's just how we tend to roll from here to the end of math, is we stick with the radians just because they work out nicer with units. Now, even though I know the sine of 150 degrees, or 5 pi over 6, is also equal to positive 1/2, I can't get those answers out of inverse sine. So this is the only number that can be outputted from this function. Our inverse sine of negative square root of 2 over 2. So let me just kind of remind you, all students take calculus. This is our sine and tangent. So negative square root of 2 over 2. I look for our inverse sine. It's either in quadrant 1 or in quadrant 4. It's negative though, so we're going to have to go with quadrant 4. So our negative square root of 2 over 2, like hopefully you recognize when we've got all the 2's, this is our 45-degree angle, when two sides of the triangle will be equal. All right, so for our sine, on the unit circle, this is 7 pi over 4. But our thing runs from negative pi over 2 to pi over 2. So instead of measuring the 7 pi over 2, we're just going to measure it backwards as negative pi over 4, which is negative 45 degrees. So what you do with the negatives depends on which function you have for what answer you're going to get out. These are the kind of things you can technically punch it into the calculator and get a result. And if your result is going to be like something like negative 45 degrees, cool. It'll spit that out for you. But other times the answer might not be so pretty, and you still have to understand like where this angle is in the problem you're doing. What does it mean? All right, our cosine. Remember, cosine's our other guy, so it's defined here. Cosine's negative in quadrant 2. And cosine is long here. So that is our 30-degree reference angle, which is our pi over 6. So a little bit less than a whole pi is 5 pi over 6. That is our angle here. And then inverse tangent of +1. So remember, arctangent, quadrant 4 and quadrant 1. Quadrant 1's where it's positive. So tangent is 1 when the sine and cosine are equal. And they're equal with our 45, 45, 90 triangle. So this is pi/4, or 45 degrees. All right, I'm going to cut it there and then start another video.